All right, so chapter 2 is devoted to studying linear and quadratic equations, right? So these, certainly linear equations, if nothing else, you're definitely familiar with. Quadratic, I'm sure you've seen as well, but probably they're a little bit more difficult to solve, so you might not remember as much about those as you would linear. So we're going to do this in two pieces. 2.1 is devoted to studying linear equations and inequalities, so we'll learn all about those. And then in section 2.2, we look at some word problems involving those types of things. And then we'll move on to quadratics after that. All right, so to begin, let's look at section 2.1, the properties of equations, right? So these are things that you've been told when you were first studying linear equations about balancing both sides, right? So if you start off with an equation, A equals B. So do you have two things that are equal? You're allowed to do two things to both sides. You can add or subtract the same number from both sides, and you can actually multiply both sides by the same number, assuming that number is not zero, and retain the equality. Right? So those, you're always allowed to do that to both sides of an equation. So using that idea, let's actually look at example 1. Right? You have to solve this equation, 3x minus 1 equals x plus 5. Well, the idea would be to solve that. It means that you want to find the value of x that when you plug it in gives you a true statement. So for instance, if I were to plug in 2 in for x here, if you plug a 2 in on the left-hand side, you get 3 times 2, which is 6, minus 1, that's 5. But on the right side, you get 2 plus 5, well, that's 7. Clearly, 2 is not a solution because it didn't result in a true statement. So what we want to do through using these two properties and the properties of algebra is to be able to find a value of x that when you do plug it in, you do get a true statement back. To that end, the idea is to get all the x terms on one side and then all of the constant terms on the other, simplify both sides, and then divide by the coefficient of x. And so that's what we do here. If you follow the steps, I'm going to choose to move the x's to the left side and the constants to the right. And so to do that, I'm going to add 1 to both sides of the equation here because it removes it from the left, because -1 plus itself is 0. And in effect, it adds it over to the right, right? So you've moved it over. Similarly, if I want to move this x to the left, I'm going to subtract x from both sides because, again, it removes it from the right, given that x minus x is 0. And on the left, it becomes 2x. At this stage, I want to find the value of x that makes the original equation true. Well, if I didn't have that coefficient there, I'd have the value of x I wanted. And so what I'll do is I'll multiply both sides by 1/2, or said differently but equivalently, I can divide both sides by 2. If I do that, I get x equals 3. If you were to plug x equals 3 in to both sides here, you'll notice that you get 8 each time. So in fact, it's a solution. All right, go ahead and try to solve your turn 1 and see what you get. All right, so now if you go through that, what I want to do is the same idea. I want to get x's on one side, constants on the other, simplify, and then divide by the coefficient of x. But to do that, I need to distribute this negative sign through, right, to both terms, not just the first one, but to both terms. Once I've done that, I can combine those two constants, right? So I get 30 plus 6x equals 0. And now I have to have the x's on one side, the numbers on the other. Here, they're both on the same side. And so I'm just going to choose a side, or choose one of these to move to the other side. Let's say I'll move the 30 to the right. I do that by subtracting 30 from both sides. That gets rid of that 30, leaving only a 6x on the left, and now a negative 30 on the right. If I now divide both sides by 6, I get the value of x equals -5 as the solution. Same idea here. You can go ahead and try this one before we talk about it. But same sort of idea, you just have more grouping symbols to deal with, but it's exactly the same premise. So go ahead and try solving that and see what you get. All right, so now if you do that, what I've done here is, this is just the equation. I'm going to distribute the 3 through both terms of this parentheses. That would give me 3x minus 12, but minus 12 plus 3 is minus 9. And so I get 3x minus 9 on the left, and doing the same thing on the right, but I didn't write all the terms out, but you can supply the details there. Multiply both terms in here by 4, both terms in here by 2, add the constants and the x term separately, and that'll give you minus 2x plus 56. At this point, you want to choose a side to make the x's go on and the constants on the other. I'm going to move the minus 2x over to the left by adding 2x to both sides. And I'm going to add 9 to both sides to move that negative 9 over. The minute I do that, I get 5x equals 65. And so now if I divide both sides by 5, I get x equals 13. All right. So notice, same idea. We have to use distribution sometimes and adding like terms, but that's basically the only wrinkle that you have, right? Always it boils down to an equation of the form something times x plus a number equals something times x plus a number, and you do the same sort of idea. All right, when you have an equation that involves fractions, the first thing you want to do is get rid of all the fractions by multiplying both sides by the LCD of all fractions that occur on the problem. Now, you'll ask, do I have to do that? And the technical answer is no. You can leave the fractions in there, but then you have to deal with subtracting and adding and dividing fractions, which not only is tedious, no one likes to do it anyway. So if you can avoid doing that and work with whole numbers, you would, right? And so that's what we're going to do. The LCD of all the fractions involved in this equation is 6, and so I'm going to multiply both sides by 6. Okay. When you do that, remember to distribute that 6 through both terms on both sides of the equation, right? And in effect, notice that given that it was a LCD of all the fractions, every time it's going to kill off that denominator just by choice. Right? Once you've done that, notice you get an equation of the form that I discussed before. So to solve that, you move the x's to one side and the constants to the other. And then the minute that you do that, which I moved here, actually all I did here, so this is a superfluous step. You really don't need this step here. All I did was swap the sides. I'm not even sure why that happened. But if you just take the 4x to the right and the minus 5 over, you get this equation, divide by -1. So actually just this equation, that one right here, that middle line, that third line there, just throw it out. All right, you go ahead and try your turn too. Hopefully it goes a little bit smoother than what I just talked about, and see how you go, what you get for that. All right, so notice that it contains fractions, and so the LCD of all fractions involved is 4. So I'm going to multiply both sides by 4. Remember to distribute that 4 through both terms each time. That results in this line. When you multiply here, you get rid of that 2 into that 4, but remember you're multiplying that number that results, namely the 2, times the entire numerator. So you want to put parentheses around that to remind yourself to in fact distribute that 2 through both terms. Same thing over here, only now this time it's 1, so there's not a big struggle. But the same sort of thing would occur here if this had been anything but 4. All right. Once you distribute this -2 through, simplify both sides, and that will actually yield this equation. So to find x, all you have to now do is move the 9 over and multiply both sides by -1. So you get 11 as the solution. All right. I'll leave you do this. It's the same sort of idea, but now you have fractions inside of fractions. Just try doing that and see what all you get. I'll put the solution up there just so you can see it and check yourself. All right. Sometimes you're going to deal with equations that don't involve actual numbers, but they involve what we call parameters. All a parameter is a variable that's used, or a letter that's used to represent a number, right? And so here, anytime you have formulas, if they're in economics, biology, chemistry, any sort of field that uses any mathematics whatsoever, you're going to encounter a formula at some point. And in this case here, the idea would be to solve for x. And so you treat it the same way you did above, pretending that A, B, C, and D are all actual numbers that you can deal with. The same premise is at work here. I'm going to move the x's to one side, the constants to the other, simplify, and then divide by the coefficient of x. So if you do that, notice what I did is I moved the cx to the left and the b to the right by subtracting them each time. These two terms on the left are like terms because they have the same variable part. And so I'm going to yank the x out, right, to get that quantity as the coefficient of x equals the right side. And now assuming that the coefficient's not 0, right, because you can't divide by 0, I'm going to divide both sides by it. That wipes it out over here, and I get that x is equal to that fraction, which is a number because there are no x's involved. Okay? So that's called a literal equation or a formula. Right? This one you've actually have seen before, and we'll see it yet again in upcoming sections. This is what's called the point slope formula for a line. And just suppose you want to solve that for x of 1. Right? Go ahead and try that and see what you get. All right, so when you do this, the only way to get at the x1 here is to first multiply through by that m, or you could technically divide both sides by m if you want, right? But I'm going to go ahead and distribute so I can avoid fractions for as long as possible. If you do that, you get this equation, and I'm going to move the mx to the left by subtracting it, right? That isolates the x1 term on one side, everything else on the other. And so all I have to do now is divide both sides by the coefficient of the variable I'm trying to solve for, which is x1. So I'm going to divide both sides by minus m, and that yields that fraction. Okay. Example 6 is another common formula for Celsius and Fahrenheit. I'll let you go through and look at this one. But it's common to actually have to go from one to the other, especially in chemistry classes. And then your turn 4, I'll let you read on your own. Okay, now let's turn our attention to linear inequalities. Sorry. All right, so for inequalities, notice that you can still add or subtract the same number to both sides and you retain the inequality. And if you multiply both sides by a positive number, you retain it. But here's the difference. If you multiply both sides of an inequality by a negative number, the inequality sign changes. And that's really a property of ordering that we talked about earlier. But you just have to remember, whenever you multiply or divide both sides of an inequality by a negative number, you switch the sign. Okay. Otherwise, the exact same approach used to solve linear equations is used to solve linear inequalities. No difference. All right, so for example, suppose we want to solve this inequality. The idea is to get x on one side by itself. And so to do that, I would move the 3 over, as I did here, and then divide both sides by 4. Since it's positive, I do not change the inequality sign. And so I have x bigger than minus 11/4. So there's an entire array of values that actually serve as a solution this time, whereas for a linear equation, you had a single solution, right? And so here we get what's called a solution set, and it's represented by everything to the right of minus 11/4 on the number line, not including a negative 11/4. And we know that we can represent that using interval notation, right? Everything to the right of minus 11/4. Okay. Go ahead and try this one, see what happens. 7 minus 3x less than or equal to 19. All right, so the idea again is to get the x term on one side by itself, right? So I'm going to move the 7 over by subtracting 7 from both sides. That yields the inequality minus 3x less than or equal to 12. And so now if I divide both sides by negative 3, remember, if I divide by a negative number, I have to switch or reverse the inequality sign. And so if I reverse it, it becomes x bigger than or equal to minus 4. Notice I'm including the minus 4 here because of the equal sign. And so this time I use a bracket, not a parenthesis, on the -4 to infinity. All right. Just as before, this is the same sort of encounter that we have with equations. You could have inequalities that involve fractions. Fine. You can clear the fractions in the exact same way, multiply both sides of the inequality by the LCD of all the fractions that occur in the inequality, and then just solve like you normally would. Right? So I'm going to let you look at this. I'll show it here so you can pause the video and check yourself. But go ahead and try that one and see what you get. All right, and that brings us then to the homework. So I suspect this section probably is not going to cause much heartburn. Some of these problems with decimals or with radicals might cause a little bit of pause, but I suspect you'll be okay with it. If not, refer to the video supplement list and check out some more videos of solving these equations and inequalities. Let me know how it goes.